All right, we're cooking. Off we go. So, let me remind you where we ended and what the goal for today is. So, we wrapped up this whole optimization section, more or less, last time, which was just how to minimize a function, and the function was the empirical risk. And we wanted to minimize it over a bunch of functions in a function class, which we said is, because of the way we chose the function class, ends up being the same as just minimizing over a vector, where that vector is our parameter or a weight vector describing every single function in our function class. Okay, so that was what we were trying to do, and then we talked about the closed form solution and using gradient descent. And what we found is that with, there's various versions of gradient descent, but kind of the story was that as you increase the number of epochs, then you minimize the empirical risk better and better. You make it smaller and smaller, assuming you chose an appropriate step size. Okay. And then we said, well, you know what? Although we do this, we're going to kind of reach a best performance because we only limited ourselves to lines originally. And then we're like, well, maybe the data might look like this. And so we don't want to just fit lines to the data, but we might want to fit more complicated looking functions like a quadratic or something of a higher polynomial power. And so we said, why don't we allow ourselves to pick function classes that contain more richer functions? Because you can see here, the purple function will fit the data better. And thing to keep in mind is the theme for the next 5 minutes before we get into the next section, which is all we're talking about is fitting the data in our data set well. That's all we're talking about right now. How we do on new data is going to be the discussion in a moment. So really, we're just trying to fit these data points well. And the story was that there's, wow, this looks really dense, but really all that you need to know is that there is now this feature map. That's this phi. Maybe I should give it a name. So this guy, wow. This guy is usually called a feature map or a feature function. And it takes your original features and maps them to more, I guess, expressive, interesting, whatever, representative features. And usually these will be kind of chosen for your problem of interest. Polynomials aren't the only choice, but they are the only ones we will study in this course. There's all sorts of other ones that people choose, like you can use these what are called the radial basis functions and so on. And there's a lot of research that went into like these kind of different types of feature maps you can use. And all of them are doing the same thing, which is trying to kind of give you new kind of behaviors that you can model of your original features. Okay, and so the function class, for instance, F2 will now use polynomial features up to degree 2, up to and including degree 2. And it's the same kind of definition as before. You just replace the original features with the feature map. And now your parameter vector gets larger because now it's multiplying new features, such as like this x1 squared. That was the high-level takeaway. And what that allows us to do is, allows us to model functions like this now. This would be like the squared function. So this would live in the calligraphic F2 function class. And the observation we made after doing all of this is first that the function class F1, F2, F3, they're strictly increasing. Each class has kind of more functions than the previous. And what that implies is now if you're minimizing the empirical risk over these function classes, well, you could do no worse than before, assuming you pick the optimal, like the correct optimizer. If you really find the true minimizer of the empirical risk, well then, and these are assumed to be the true minimizers, well then you can do no worse than before, in the sense that the empirical risk for a line, the best fit line, will always be at least as large as the best fit like quadratic, which will be at least as large as some higher order p polynomial. So as you pick more and more complex functions, you're only making the empirical risk smaller and smaller. Once again, always assuming here that we've picked the actual minimum. And that would be kind of like running gradient descent for a very large amount of epochs, and you've kind of gotten to the minimum. And visually, and we're going to study this a lot today, but visually, what we kind of left off with is that if the black points were your data points, this was your data set, you had 5 points only. It's a small data set, but if you keep increasing the kind of the type of function you're using, if you started with a line, maybe you don't fit the data set very well. If you allow a quadratic, you can fit it kind of better, and if you allow a very large power, then you can fit it basically perfectly. However, we left off with this observation that although we can fit it perfectly, maybe this is not the desired kind of predictor or model we want, because on new data, such as these orange points, we'll actually do quite a bit worse than this purple function for some reason. Okay, and I'm gonna this was the second order polynomial. And I just want to make that a little bit more clear with one more plot, which we will constantly be referring to and adding new kind of functions to it to understand the different relationships of things. So I just wanted to make this kind of very clear. And the plot is going to look like this, which is, okay, I'll move this down. We'll talk about this in a moment. The x-axis is going to be the power of the polynomial, the degree of the polynomial. And the y-axis is going to be the empirical risk, or the estimate of the expected loss for that power of f hat of p. And once again, we're here assuming this is indeed the minimizer. Maybe I should make that absolutely clear. So f hat of p is equal to the arg min f from the function class f of p. So these are polynomials up to and including degree p of L hat of f. Okay, so this is the true minimizer. And the observation is as follows, that we're going to have a plot that looks like this, which is if we look at the different degrees, maybe this is degree 1 polynomial, this is 2, 3, 4, 5. What this expression up here was showing us is that we're going to keep getting smaller and smaller empirical risk. So it's going to look like this. Yeah. Sorry. Yeah, okay. So that's the plot to keep in mind. And eventually you can get to 0 if you pick a high enough polynomial, you can fit the data perfectly. Okay, cool. And so we're gonna kind of answer in the next chunk of this class, like the next topic is going to be why, once again, this may not be a good idea if you want to do well on new data. And kind of at what point do you stop? And things like this. But before getting there, I also wanted to kind of jump back and answer a topic we discussed before, which is like, what's the point of introducing these polynomial features, especially when you have kind of these higher dimensional features. So if d equals 2, then you end up with features that look like you have this like x1 times x2 kind of term. And so I think I thought of a better example. So let's just talk through the example and see what happens. And somehow I lost my notes from yesterday, so we're going to just do this from this random thing I had left over here. Anyway, so the story goes as follows. Yeah, so you're going to have these features. Let's say you had 2 features. The first feature is x1, and this is going to be like your number of rooms. So we're going to stick with this house price prediction thing. And once again, we're just going to try to motivate this like x1 times x2 term, hopefully in an intuitive way. And then the other one, the feature x2, is going to be the distance to downtown of your house. Okay, and we're going to make a slight assumption to make this like easier to write and things work out nicer. And we're going to just assume that we're only dealing with houses, let's say like in the Edmonton area, and let's say the farthest distance that's still considered in Edmonton is like 30 kilometers from downtown. Okay, so like x2 is going to be an element of either exactly centered in downtown or at most 30 kilometers from downtown. And this is, of course, still a subset of the real numbers, which we assume our features are in. Oops. And then the number of rooms, well, this can be like any number, 1 up to anything. And that's also a subset of the real number, so we're all good. And so we're predicting these house prices. So now I just wanted to like motivate what a, okay, move this guy down. What you might expect like a kind of maybe a good predictor to look like. And so maybe it looks something like this. So like we've been up to this point kind of like various times just thinking, let's just think of the number of rooms. So probably the price of a house is going to increase as the number of rooms go up. And maybe when you have like, I don't know, 1 room, it costs like 200,000. Maybe with 2 rooms, you think it costs 400,000. So the relationship would look something like 200 times x1, right? But then you might think like, okay, you know what? As I get closer to downtown, I think the price of the house is going to go up, first of all. And before we were kind of limited to doing some sort of representation like this, we would have to do like, let's say, since it's going to be kind of the inverse relationship, it's like as it gets closer and closer to 0, the price goes up. You might think that it's going to be something like 30 minus maybe x2. I don't know, times some amount like 300, let's say. So let's just interpret what this would look like. If x2 is 0, means you're in downtown. And let me just normalize this. So if x2 is 0, then you end up with 30 over 30. You end up with 300,000 extra dollars for your house. If x2 is 30, then you end up with 30 minus 30. You get 0, and you get basically there you're on the outskirts of Edmonton, and you just end up with this term. This is what we were kind of limited to before. However, hopefully, like you would agree that it might be logical to think, well, as you get closer and closer to downtown, actually increasing the number of rooms, the increase in price will go up more than just $200,000. Okay, so in other words, maybe like if you're in the outskirts of town, like a 2-bedroom house goes up to 400,000, then it goes up to 600, 800. But maybe when you're in downtown, going from like 2-room house, which maybe is, let's say, $1 million, to 3-room might increase by more than 200,000, like 500,000 or something like this. And so in other words, the amount of increase might depend on kind of both features together. Okay? And so the way we would now incorporate this type of relationship is we would add the x1 term here to multiply these. And now let's just do a bunch of like different case analysis to see how this kind of works. Okay. So let's do the case where x1 is equal to, say, 1, and x2, first case is where it's all the way on the like outside of Edmonton, that was equal to 30. Well, then what we get is just the original thing, which is like 200 times 1. And then you get 300 times 1, but then this becomes 30 minus 30. So basically, this term just goes away. So you get a house that's $200,000. Sure. However, if you move the house closer to downtown, so let's say like x2 equals 15 or x2 equals to 0, well, for the 0 case, you plug in 0, you get 30 over 30, so you get 1 times 300, and then x1 is just 1. So you get plus 300. So maybe it goes up to 500,000 if you're directly in downtown for a 1-bedroom house. And, oh, that's the case with 0. And 15 would be just in between, which is 350. Okay. Now we can do something more extreme. Maybe you have a 5-bedroom house. And now if you have a 5-bedroom house and you're, let's say, on the outskirts, then it ends up being, once again, 30 plugged in here becomes 0. So you get no increase for being close to downtown because you're really as far as you can get. And you just get the price increase due to having 5 rooms, which ends up being $1 million. So that's maybe reasonable. But now what we'll see is that as we get closer and closer to downtown, the price increase is much more dramatic than this. And so we'll do x2 equal to 15 again, and then x2 equal to 0. And if we do the 0 case, we get that we're directly in downtown, so you end up with 30 minus 0 over 30, that's 1. Now we have 5 rooms. So notice that now the claim is that the scaling is not going to be just $300,000 more because you're in downtown, but actually an increase in 5 times 300. Or another way to think about it is that if you have, for every increase in rooms, you end up multiplying by an extra $300,000 on top of the $200,000 from before. So anyways, we end up with what is the 1 million here plus 300 times 5, which is 2.5 million. And then in between is this. And so hopefully this kind of makes some sense, or you might, like, nonetheless, you might sometimes want to like model these type of relationships. So once again, if you have a 1-bedroom house and you move to a 5-bedroom house, but you're far outside Edmonton, the increase is from 200 to 1 million. But if instead you had a 1-bedroom house in downtown and you upgraded to a 5-bedroom house in downtown, that could increase you from 500,000 all the way up to 2.5 million. Okay, so that's just kind of an in-depth story of how these features might increase. And you can imagine these higher order polynomials can be even more complicated kind of relationships between things. Okay, and then this was the same thing. Okay, and then I'll post this updated version of the notes, of course. All right, so back to the story. So let's address this problem. What do we do? Or like, what's going on? We wanted to minimize this empirical risk. We kind of achieved our goal. We can make it as small as we possibly want. And it seems that we're still not getting the behavior we want. And so somehow we clearly need to relate this to how we do on new data. And that means really relating it to the true risk. That, like, not L hat, but the actual L of this thing. And that's what we're going to do in these next lectures and kind of discuss about how to pick the function class and how to do that. And then some more kind of elegant way of moving between the complexity of functions that's not just choosing a different polynomial each time. Because let's just keep in mind, if you were to like try, like you have access to this, right? When you run your algorithm, you run the algorithm, whatever, you run gradient descent for, let's say, a couple thousand steps or something, you'll get this number, and then you'll get it, and you can plot it like for degree 1. But what's happening here? Well, what's happening is you would literally need to run the algorithm with a function class that uses degree 1 polynomials once. And then you would have to rerun it again using polynomials of degree 2, which is literally rerunning ERM with a totally different function class, right? And then you rerun it a 3rd time, and you can plot all these things, and you can be like, oh, okay, I see this plot, whatever. And this would be like one of your hyperparameters. It's similar to how you would have to rerun it for a bunch of different step sizes if you wanted to find which step size gives you the fastest kind of rate of progress, which we saw earlier here, this was the number of epochs. And this dotted line is one of the points that we saw earlier down here. So that dotted line would have been exactly this point. It would have been the best possible performance we could get when using a good step size and running for as many epochs as we possibly can and really getting to that minimum. And then the dotted line would have been different for a different function class and so on. Okay, so let's let's get into what I'm talking about. What is happening? Okay. So, to begin, so the whole story is we're trying to somehow talk about evaluating different types of models and kind of like choosing between different function classes and so on. Sometimes it's called like model selection or evaluating models or function class selection. So I don't know, we're going to give it the following name, which is evaluating predictors or models. And that's what we're going to talk about for a while now. Okay, so let me kind of remind you of some things. So we have a learner. That learner takes in a data set. It outputs that f hat. And for like this entire set of kind of lecture material, we're just going to, from now on, assume that, well, actually, I guess I can write it here. F hat is just always going to be the minimizer. And we're just going to assume we've actually done the optimization appropriately. We've really reached the minimizer, something really close to it. And we're just going to study whether that was like how that does. So this is really going to be the argument f in the corresponding function class we're working with, right? Of the empirical risk. We've seen this. This is exactly what we've been doing. Okay. So that's that. And let me just remind you some things. This L hat of f is equal to the sample mean from I equal 1 to n of whatever loss you use of the predictor we output. Well, here it's f of xi, our data point, yi, and that's it. Yeah. And that's the empirical risk. And the true risk, which is kind of what we care about, is equal to the expected value of the loss of the predictor at a new data point x, a new feature x, compared to a new label y. This is how we would do on new data. Okay. So now we're just going to do some like kind of observations that we've seen before. But before doing that, I just want to note that this d is a random variable. And what that means is that if you change as d changes, like if you got a different data set, and let me just like mention in two different ways. So like, of course, we get a data set, and then we're going to run our algorithm on the data set, and then we're going to get a predictor, and that's what we're going to use. But the hope is that, you know, your algorithm doesn't only work for a very specific data set. You know, it's like maybe you want to use your algorithm, by algorithm I mean your learner, in Edmonton and gather data there, and then maybe you want to like, you know, sell your like learner and be like, you can if you're in Toronto, you can also use this, and if you're in, I don't know, London, you can also use this. And so, you know, similar to many other fields of computer science, you kind of want an algorithm that works on many different kind of settings. And so that's why there's this kind of emphasis on we want to work on like different kinds of data sets, okay? Or like if maybe I gathered like data set in Edmonton, someone else gathers a data set and it's different, I'd like to guarantee that his still works fine, or hers. Okay, so there's this idea that like I'd like it to work kind of on different data sets. And so if the data set changes, right, since it's this randomly gathered thing, our predictor will also change, and we're going to want to kind of guarantee that it does well in expectation over data sets, and we'll talk about that in a moment. And just to make this very clear that, you know, this f hat is depending on the data set, that if the data set changes, f hat is changing. I'm going to subscript it with d kind of from now on to make that very clear, that this predictor depends on the data. And so when we look at a quantity like this, and we plug in f hat of d, well, then the following quantity here, before we had that these were like IID, they are independent and identically distributed. Well, now we end up with this whole issue we're going to see in a second, which is that we're taking a sample mean over these n points. However, the actual function inside here itself depends on all of the other points in the sum. And so there's going to, and this is exactly what we kind of saw with this like overfitting and business that we saw before. So anyways, let me draw some pictures now. You'll see that this class will be kind of half an art class, half a machine learning class. There's going to be lots of plotting. And hopefully you'll give a bit more intuition about all these things going on. Okay. So let's start with the first easy case, which is like kind of the usual way statistics is done and where things work well. And we've kind of talked about this in several ways before, but it doesn't hurt to kind of continue making the point. So there's features on the x-axis. I guess they're one-dimensional features. And here's the order of operations of how things are going to work here for this case. First, this is how statisticians would like you to do things, which is like, suppose we pick okay, let's just do, I don't know why I'm writing long sentences here. This is going to be the process. Pick some function in your function class, right? So let's do that. Let's pick the function. Pick any function. You pick that first. And then you need to gather your data. Okay. This is the order of operation. Pick the function first, then you gather data. And in other words, in probability terminology, this would be equivalent of saying that f is chosen independently of d. And so in reality, you really could gather the data first and then pick the function, but you better not pick the function based on the data. So it can't have anything to do with the data. Okay. And in that case, what you end up getting is actually quite a good kind of understanding of how your function does on new data, right? Because if we look at the plot, what that would look like is above you pick the function first, and then you gather data, and maybe the data looks like this. And you'd be like, okay, I guess I don't know, I can measure different things. I can measure this, for instance, the empirical risk of this function, that squared distance, let's say, when I use the squared loss, and I'd have some measurement of how it does kind of on fitting this data. And hopefully you're sort of convinced that this would actually give you a reasonable estimate of how your function is doing, but with this caveat that the function was chosen independent of the data. And we really studied this kind of situation already, and we saw that if that is the case, well then we had the following kind of guarantees, which is that the expected value of the empirical risk of f is exactly equal to the true risk of f. And this was just that expanding this out and noticing that it's a sample mean, and that everything is independent and identically distributed since f, your function, is fixed and you're only talking about that single f. And we also saw the property that the variance, right, of L hat of f decays as 1 over n. So as you get more and more data, you get a better and better estimate of kind of how this function actually fits to new data. Yeah. Okay. And that was all good. But of course, you can see that, as we've discussed before, which is that this is not the way we're doing things, right? Which is that we are gathering the data first, and then picking f hat, and here the subscript d is very informative. F hat is based on data, right? Picking f hat from our function class based on data. Okay. And in other words, this is in contrast to before, because now f hat of d depends on the data. And just to make that clear, let me make this even more clear. I'm going to erase these points and put less points so that it's more obvious what's going on. So let's suppose the points were like this, 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 I don't know, this. Okay. And now the procedure looks like this, right? Which is, first we gathered this data set. Of course, in reality, this is going to be a much bigger data set, but the point is here, we have 5 points in our data set. And then after gathering this data set, we then pick the function, which is that f hat of d. And so we go ahead and pick the function, and if our function class is rich enough, we really can fit all the data points, which we've seen before. And so maybe we'll fit the data like this. Right? So first we gather data, then we fit the function. And you can already see, as we've talked about before, that if I gather new data, maybe it'll be like this. And if we do, if we measure the squared loss on these new data points, they're much larger than on the actual data sets, data points. Okay. And of course, this is because we picked the function based on the data. So what's the story here? When is this okay to do? When is it a good idea? What's the relationship with how much data you have? What's the relationship with the function class you picked? And it turns out the relationship is quite nice. And there's going to be kind of a trade-off between the function class we picked for two kind of cases. So first of all, here's the first thing you need to know. So like in general, the following is the case. So we're talking about what's the expected value of our, our empirical risk, and now of f hat of d. And before we had this, right? We had that this was equal to the actual risk, the true expected loss of this predictor. But like visually, we can see that cannot be like that. That's clearly not becoming the case anymore. Let me just drive the point home. In the previous case, suppose like just to make it clear, like suppose you did gather this data first, and then you picked this function independent of it. It didn't matter. Well, then if you gathered new data, it's probably going to look something like this. And you can see that, on average, the error of that new data is going to be about the same as before. So nothing is really changing. But in this case, it's going to be much smaller. And so in general, this no longer holds. So they're no longer equal. And actually, we're going to see that this is always smaller. And it's how much smaller it is going to depend on something. And the other thing is that this quantity here is now a random variable. It depends on how d changes. And so we're going to actually need to compare this to the expected value of this. But don't worry too much about this step. Okay. So this no longer holds. And the reason why is because, well, these kind of points that we've been using for the sample mean are no longer IID. And so the property we really needed before was that each one of these things, each one of these points in the sample mean, when you write it out, they look as follows. It's like little l, the loss of f hat of d of xi, yi, and you had a sum, a sample mean of these endpoints. And for this kind of property to hold, we needed that they were independent and identically distributed, but they are no longer IID. And in particular, to make it very clear, this FD depends on all the data points, probably, right? Depending on what learner you use, it's going to depend on all the data points in general. So this will depend on like x1, y1, all the way up to xn, yn. And so you no longer have this kind of property. And so the question is kind of like, what does this relationship look like? And we're not going to go through like the proof or the details of this, but I'm going to kind of give you the properties that you should know, and we can hopefully build some intuition why this would be the case. So it can be shown that the following is true. So we're going to compare these two quantities. And it's actually going to be the other way around. So this is our true kind of risk. This is the thing we want small. And this is the thing we actually kind of minimize. We're going to take their difference, and we're going to ask, how large is this difference? Right? And you should keep in mind, this is thing we're making it as small as possible, really. So we want to ask, like, kind of how much smaller is this than this? And so there's like, so it can be shown that this is the following holds, which is the first point is that this guy here, or the thing we actually minimize, will be less than or equal to this. And that's just by, well, various ways, but like you can visually see by observation that since we're fitting the data points, we're going to have a much smaller kind of value or estimate of this empirical risk than the true expected risk, because we're fitting the data better than we probably will on new data. Of course, for a particular data set, we might get unlucky, and actually this could be small, could be larger than this. But in expectation over data sets, this will indeed be the case. And we'll kind of see this for a particular data set soon. So that's the first kind of property. The second property is that, okay, so this is where it kind of becomes interesting. Oh, and maybe I put this in words as well, which is that quantity above is non-negative. So it's always positive or 0. And just in other words, that means this. Okay. But we really care about like how much larger is this, right? What's the difference? And here's how that difference scales with different changes. So first of all, this difference will increase, so it gets larger. It increases as the function class gets more complex. So unfortunately, as we increase the polynomials, like the degree of the function class, we get a more complex function class. And we saw that this term gets smaller and smaller, right? That was that plot we just saw in the end of the last one. And we're going to talk about that. But unfortunately, the difference, which is the error to the real risk that we care about, actually grows with the function class. And that should intuitively make sense. The more complicated the function class, the more you're going to fit the data well. But compared to new data, you're going to be further and further kind of from being like, well, at least your measurement of it is going to be quite off. Okay. That's the first property. The second property is that it decreases, so we can actually decrease this error if we increase n, or as n, the number of data points. Okay, so this is really quite an important observation. So increasing the number of data points can really only help you, because then you can see like here we have 5 data points, and you can really allow for this kind of behavior. if you had a bunch more data points, it's very hard for your function to like extremely well fit this thing unless it's extremely, extremely complex. Okay, so increasing the number of data points is always a good idea. However, increasing your function class size has this kind of trade-off. And visually, it looks like this. Like this is going to be the plot we should have in mind, which is the plot we ended the last class with. Or I guess we ended the last lecture, kind of the last lecture section with, which I just drew. And now we're going to introduce one more kind of line to it. And it seems the colors I have gone with. So, okay, just let me remind you, we ended with like the following kind of plot. And well, we're going to have different things we're plotting, so I'm going to leave the y-axis empty. Okay, so we ended the last section with a plot that looked like this, which would be like, really, let's just understand this one more time. You run ERM with a function class of polynomials. Okay, let me just write down what we're plotting here. So recall now we're going to use f hat, which depends on data, and it's going to depend on the polynomial degree you use for your function class, right? So I'm going to put two things here. This is going to equal to the minimizer, which is the solution to your ERM problem, right? Of f when you use the function class of polynomials of degree p. Okay, so this is how things differ. Let me just make some room. And you're minimizing the same empirical risk. Okay, so let's just first of all understand what is this f hat function. This f hat, if you change p, you really rerun the algorithm, but with a totally different function class, right? Bigger or smaller, depending on if you made p bigger or smaller. And what we're plotting here is going to be the corresponding empirical risk we get when running for that corresponding p here. Okay? So I'm going to plot these points. So like we saw in the previous thing that it might look, maybe the plot looks something like this. So you run it first for like p equal to 1, then 2, then 3, 4, and so on. You might see something like this. And so, yeah, we can just draw, we can draw the curve to make the kind of it clear that it's decreasing. Oh. And of course, when you run it in practice, you're going to run it on one data set. But it turns out that like the same kind of trend and property, and we're going to study this, holds when you do it over the expected value over data sets. So this is the empirical risk in expectation over data sets. So if you run this for a particular data set, it can be the case that you end up with like this maybe slightly higher and then this one lower. But on average, this is actually the trend you're going to see. So once again, for any particular data set, this might not quite be the case sometimes, but in expectation, you will see the following. And okay, so now what's the new part? The new part is how does the real risk look like, right? Which is this quantity here. Like how do we actually do on new data? And the plot for that will look as follows. So as we saw, it's always going to be larger than what we minimized because we're always trying to fit the data. So at the beginning, it might be something like this, and they might be pretty close for this less complex function class. Then it might kind of, be farther apart, which is the observation we saw. And then it might, still be further apart, but still less than before. So like, notice the distance, like this distance is growing between each of these. However, it's still going down. And then here, maybe still it's like over here. So it's a bigger difference, but still lower than before. And then you might start observing that this difference is large enough that it's even worse kind of than before. And so you'll see a plot that looks like this. Okay. And so what we're plotting here is the true risk of our predictor on average over different data sets. Okay. And so once again, let's understand this relationship. So as we increase the polynomial degree, we are minimizing the empirical risk, and it only gets smaller because we're picking bigger function classes. So it can only find a better minimum to this quantity. That's why it's decreasing. However, what you find is that, unfortunately, as the function class gets more and more complex, the difference of your empirical risk calculation and the true risk, the actual thing you care about being small, how you do on new data, is growing. So this difference keeps growing and growing and growing and growing and growing. And you can see that there's kind of like some sweet spot where the difference is growing, but since this kind of empirical risk is going down, this will also go down enough, hopefully. And then this would be kind of like your best choice of polynomial degree to use, and then it would get worse and worse. Okay. And so visually, we've kind of like what we saw here is if the polynomial degree was like 7, then that was the case where you overfit the data like this. And if the polynomial degree was a lot lower, then that would not be quite the case. And so when you look at a plot like this, the kind of terminology that's used is that here you're underfitting on this side of the plot. Over here, you're overfitting. And this is kind of like you're just right. This is like the best choice of polynomial degree that you can make. Okay. So far, that's like the relationship for this polynomial degree. And this is a general trend in terms of the complexity of your function class. So if you use like not polynomials, you can change your function class to what we'll see as neural networks later. Well, we'll see one lecture on it. And you can pick different size neural networks. And the bigger the neural networks, the more complex it's going to be. And there's like a similar kind of story with the neural networks. If you pick a really big neural network and you have a small data set, well, then roughly speaking, this is the behavior you're going to see. And you can try running different size neural networks. You can kind of that could be a hyperparameter, let's say like the size of this thing. And then you'll find that there's kind of like a size of a neural network that's just right. There's definitely more to it for the neural network world stuff, but that's the rough idea that you should keep in mind. Okay, so this is the relationship with complexity of the function class. The other relationship we talked about is data. And thing to keep in mind is we're trying to like kind of build some intuition of like, what function class should you pick for your problem? Should I maybe pick something more complicated or less complicated? And the other thing is like, should I go and gather more data? Is it worth my time and stuff kind of? And gathering more data will never hurt. And the trend for gathering more data will look like this. So for gathering more data, we'll need to fix some polynomial degree and look at how increasing data goes. And the thing that should be mentioned here as well is in the case above, we had to fix a size, like a data set size. So the data set size is obviously not varying. So here we fixed n. So the size of the data set was fixed, and we varied the polynomial degree. Now below, we're going to vary the data set size and fix some degree polynomial and see how that affects. Well, how that affects this difference exactly. And so let's look at this just right point, fix the polynomial degree to 4, and see how increasing the data will cause things to vary. Okay, so we're going to say, let's say, fix p equal to 4. Maybe up here I chose to fix n to 100 so that we can see where the points match. So this is the error when you have 100 data points. Okay. And the x-axis here is going to be now 10, 100, 1,000, 10,000, and so on. That's good enough. Okay, and let's plot these two things. So with 0 data points or 1 data point, you're going to get 0 error for the empirical risk. And well, let's plot the point we already know. So this point over here is with 100 data points, and we have an error of something like this, right? And so that means that this point is going to correspond to somewhere here. This point is going to correspond to somewhere over here. And so we can plot those two. So this would be this. This would be something like here. And this difference would match this. And now the question is, if I fixed my polynomial degree 4 and I increase the data, how will this relationship differ? And of course, you could do this for any degree. And the relationship is as follows, where you're going to find that these get closer and closer. So you're going to find that this will decrease. This will probably increase like this. And so they will kind of converge. Right? More data points means it's much harder to overfit and get a very, very small error. In the extreme where you have, and I probably should put the case where you have 10 to the 0, which is 1, you can fit perfectly with any function. You just go right through the point. So you're going to have 0 error there. Then you need to fit 10 points. That's going to be harder. My error might be like this. Fitting 100 points is even harder, and so on. So this will increase. And the corresponding error in the true risk will actually decrease. And so this error is shrinking each time. So gathering data points is always a good idea. Well, in terms of like, if you forget about how much computation it takes to do this, okay, so that's the relationship of the data points. Yeah, so that's the two big takeaways of kind of picking the function class and the data set size. But in practice, like how does, so, okay, we've had this relationship. What are these two things? Well, it's the same thing we've seen before. Let me just label them properly. This guy down here is this. Okay. But in practice, you only have one data set, right? And you run your empirical risk minimizer on your data set with whatever batch gradient descent or whatever you want. You minimize that. And you really do see a plot kind of like this. Like it does keep decreasing. And the question is, which polynomial degree should you pick? Okay. We clearly don't have access to this. We don't have access to the true risk. We don't have access over the expectation over all these data sets. You only have your one data set. And so somehow we're going to want an estimate of this quantity to somehow pick the correct point of your polynomial. Like basically, how do you decide on what degree polynomial to use with your fixed data set if you have no idea what this curve looks like? And so that's what we're going to try to address next, which is this kind of gave us this idea that like this is the relationship we have with the complexity of the function class. In practice, we have one data set. How are we going to kind of choose this degree of polynomial that we're going to want to use? And in general, the complexity of the function class. Okay, so the problem is that like in practice, we only have a fixed data set. Okay. So how do we tell if we're overfitting, we're underfitting, and whatnot? And in other words, how do we get an idea of what this quantity is for our particular data set? And the idea is quite simple, which is we go back to the very beginning of this section, and we look at the wonderful news we have, if we pick the function class and then gather data. Okay, so now let me kind of in words describe what is a very intuitive process, I think, which is you have your data set, you run your learner on the data set, and you fit the data like super well, whatever. You fit the data. Now you want to know, well, if I get presented new data, how well am I going to do? Right? Maybe you're at a company and your boss comes up to you and it's like, okay, you got this great thing, it fits, it does really good, on the empirical risk, like you basically got zero empirical risk. How well are we going to do on new data? And you also ran it on a bunch of different polynomials. Which one should I pick? Like for each one of these, you generated a new predictor. This is its empirical risk. Like which one should you pick? So somehow you want to evaluate what that's going to be. And here's the answer. You go out and you gather completely fresh data. And then you see how your predictor that you produced fits. And that would be the exact process that we have here, right? Which is like you had a data set, you picked your predictor based on the data set. That overfit the data set probably to some extent. And now you're like, I want to know how I do well and how I'm going to do on new data. What's the solution to that? Well, you go and gather new data in exactly this way, and you see how it's going to fit. But that new data, notice, is completely independent of your choice of your predictor, right? This is completely new data. And we're going to give this new data a kind of an obvious name. It's going to be the data we use to test the quality of our predictor. And the data we use to kind of choose our predictor is the data we use to train, okay, our predictor. And so you probably heard of these terms a lot, and we finally get to it, which is the idea to solve this problem, if we only have a fixed data set, is train on a data set, train on, let's say, D-train, and evaluate on D-test. And these are different data sets. We're going to define them in a moment, right? And let me just make this idea clear, right? You have a training data set. That's what your learner works with. It can fit that data very well and whatnot. Clearly depends on that data set. Then you go, like your learner has produced a predictor, a model, and now you go and gather completely new data, independent entirely of that process. You go and do the whole thing, and then you compare this fixed thing, this model that's already been trained, on that new data. Okay. Now, of course, the way I've phrased it is kind of annoying. Like, you go and gather your data, you do this thing, and then you're like, oh, and now I have to go and gather more data. Like, that's very unfortunate. So what you do is you just replicate this process kind of with the original data you had. And the idea is that I'm just going to take my original data set, split it into two parts, split it into the training set. Let's say like 80% is called the training set. Leave the test set untouched. Like that is only going to be used at the very end. There's this training set. So I do all this training on my thing, on that data set, train all of my different polynomial degrees, get different whatever empirical risks. It's clearly going to keep decreasing. And then I pull out my test set, and on that test set, I evaluate each one of them. And then I'll get something that's much closer of an estimate to this. Okay. So that's going to be the idea. So let's formally write down how this is going to work. So we're going to split into D-train and D-test, and they're going to look, the data sets are going to look like this. So D-train is going to look like the data set we've been seeing up to now, which is x1 up to y, or y1 up to, and now instead of xn, yn, it's going to go up to, so let me define a term, which is the size of D-train, the cardinality, the number of data points in D-train, is going to be n minus m, so less than n by m points. And the test set is going to contain m data points. Okay, so the reason I write this is so the summing notation above makes sense. So basically all I want to do is take the last m points of my data set, call that the test set, take the first n minus m points, call that my training set, and that's how I'm going to split it apart. At the end, I still only have n data points. I have just split them up. And so training set goes from x1 till xn minus m. And the test set is going to go from n minus m plus 1, right? It's the next point after this. Up to xn, which is the last point in our original data set, yn. Okay. All we did, just like in the mini batch gradient descent thing, remember we split it up into mini batches. You can think of it in a similar kind of fashion. The data set's still the same size, xn, yn, till from x1, y1 to xn, yn. We've just broken it apart into two parts. Okay, and so this will be called the training data set. This is the test data set. M is going to be a new kind of value we use. So M is going to now be used kind of for the test set size. And I guess it was also previously used for mini batch number. Okay. So now how does this procedure work? Well, it works as follows. So our learner is not going to take in just D. It's not going to take in the whole data set. It's only going to take in the training data set, which is a smaller amount. You could think of M as being like 20% of your data set. So if we had like 1,000 points, M might be 200, the last 200. And the train would be like the first 800, let's say. So you use 800 data points. You train your algorithm, like you do gradient descent. It's called training. People like to call this training or learning or whatever. Really, you just pass it into your learner. It will produce a predictor, right? And then you want to know how well is my my learner doing on like what is its okay, it's empirical risk we know is going to keep going down. Well, what's kind of its true risk? How does it do on new data? Well, then we can evaluate that learner on the test set. Okay, and so we're going to give these names like we're going to give, okay, so there's going to be the training loss, or the training, this is, people call this training loss. Really, it's the empirical risk on the training data set. We're going to say now L hat of train, which is just L hat on the training data set, and of your predictor. What's that going to be? It's just like before, but now it's not 1 over n, it's 1 over n minus m. And it's from I equal 1 till n minus m of L of f hat xi, yi. So everything's the same. This thing, you know, it chose the argmin thing based on this, and so on. Maybe I'll make that absolutely clear. So L hat train is this. Now A, what it does is it selects f hat to be equal to the argmin of this thing. F of your function class of L hat. Normally you're just L hat of f, but now it's L hat train of f. So everything looks the same, but now, based on this trickery we did, we now have a test set that we can use to kind of evaluate how is our predictor doing on new data. And so to do that, we'll now have a new quantity called the empirical risk, basically on the test set. And then the terminology people use, this is the training loss. This is your test loss. So you take the same predictor. Now you have m data points. So you take the sample mean over m data points. And now I does not go from 1 till m. You got to index the corresponding data set appropriately. So we're going to go from n minus m plus 1. Right? That's your first data point that's in your test set till n of the same exact quantity. So I'll just copy and paste to make it clear. So the only thing that changed is which data points you're using to calculate the sample mean. And the other important thing is that this, and maybe I should make this absolutely clear as well, which is that f hat depends on the trained data set, clearly. Because it's minimizing the empirical risk based on it. Right? So, and yeah, this should also, I think, be helpful. So f hat depends on the training data set. And so here, okay. And so here, since the training data set is exactly the data points that are from the indices 1 till n minus m, you can see how this depends on the data set, the data points it's taking its sample mean with respect to. While down here, you're using the same f hat, the one that was trained using the training data set, but you're evaluating it on the test data set. Okay. And that's like, visually, you should think of this as the following process that we wanted to do before, which is you gather your original data set. This is like your D-train. You fit the data using gradient descent or whatever. This will have very small empirical risk. There's like no error. Then you get your test data set, which will look something like this. And then you check the error on the test data set. And hopefully you'll agree that this will be actually a good estimate of what the true risk would look like of your predictor. Okay, and so now the plot actually does look, and you can do that. You can actually run this, and this is what you will be running in your assignments. And you can see the following kind of trend, and it will inform you on which polynomial degree you should use to run ERM and which predictor you should use at the end. In other words, you can like tell your boss that this predictor that I'm giving you not only had small empirical risk, but since it has small empirical risk on the test set, then that means that its true risk is also quite likely very, or like similar to that. Okay. And so once again, you plot, okay, I'm just going to make this, well, why don't I just take the plot from before? So we're going to go up here, take this exact same plot, and now just kind of relabel some things. So this purple guy will be L hat train of F hat on the data set, the training data set, for the polynomial P that you've run it for. Right? And let me just take this. In the plot, the corresponding is happening, which is now you're running, and we've done this before, which is now you're going to run, your learner is going to, it depends on the function class you pick, right? Each time you change your function class, you have a different learner. So if you change your function class to be a different polynomial degree, you're now minimizing over a different function class. It means your learner is also different. And once again, you should remind, this is, you're literally rerunning your whole algorithm for different sized kind of polynomials. You can think of this as like a meta algorithm, which is what people call the hyperparameter sweeping or tuning. This would be your hyperparameter. You literally rerun ERM on a different P each time. You get a different predictor each time. You're running it on the same training data set. And now you want to plot those things. So that's what this plot is. It's your, people would say this is your training loss of your model that you get from running gradient descent for polynomial using a function class of degree P. And what you will see is this decreasing trend. And then the plot, let's just erase some things to make some room. Actually, let's keep it. And then what is the thing above here? Well, the above term is now, no, you don't have this expected value out here. Instead, you have not the, okay, so this is what you want. You want the true risk, right? You want the true risk of your predictor. This is this D-train guy. F hat of D-train. That's what you want. And you imagine the plot is something like this, but you'd like to plot that, but you don't have this. Instead, what you have is an estimate of it. And now, hopefully, you're you're convinced that this is indeed a good estimate. So what do you have? You have L hat based on the test set. Right? So based on new data points, you calculate the sample mean of your predictor, your model, and this is approximately equal to the true risk, this. And the plot will look similar to the above, except now, once again, since we're not taking the expectation of our data sets, you can see weird kind of behavior. And maybe I'll, for that reason, kind of replot it to show you what. So instead of having this like perfect relationship, in practice, what you'll see is, okay, maybe here indeed you do quite bad. It's going to be above it, could be below it. Then here maybe you see, oh, okay, like I'm over here. Maybe here it drops all the way down here for some reason. Then it goes here. Then maybe it goes here. Then like this, and then I don't know, something like this. Like this is totally possible that you'll see in practice. And you'll be like, oh, what the heck happened here? Like you have this, I mean, I shouldn't be drawing. But yeah, okay, I'm not going to draw the curve. The curve is pointless. But this might be the minimizer now. And you don't have, it actually got worse, and then it got better, and then it got worse. And that's just because of the error you kind of have in this, and that you're not actually plotting this. Okay. And so yeah. And so what you would do is now you would actually pick this. You would say that, oh, this is actually what I want to pick. In this area, I'm underfitting. In this area, I'm overfitting, because there's a giant error between these things. Here it's a small one, but this, my empirical risk is really large. And we'll define this a little bit more precisely soon. And so this is the actual predictor you would pick, right? And so once again, to kind of make it clear how this, like, so now we actually have like a procedure for producing a good model, right? Which is, you have this data set, you don't really know what kind of function class you should use. In other words, you don't know if like a line will fit it well, or a polynomial of degree 2 or 3. And keep in mind, our data is probably very high dimensional, right? So you can't just plot it and see if the line is going to fit well or whatnot. So you're really kind of in the dark, right? So you have this data set and you're like, I don't know, do I use linear function class? Do I use quadratic? Do I use cubic? What do I use? And so the naive thing to do, which is actually a good thing to do, is you try them all. So you run ERM, you run your gradient descent, you use polynomial, you use function class size 1, then size, which is exactly this point. You would literally get a plot, like you're going to do this in the next assignment. You're going to run it for degree 1. You're going to get a point. You're going to run it for degree 2. You're going to get a point. Then 3, then 4, then 5, then 6, and 7. And as we've said many times, from this plot, it seems like you just want to pick this because it has the smallest empirical risk. But then you realize, well, these points are probably not good estimates of the true risk. And so to get a good, like when you actually want to deploy this thing, you want to tell someone like, oh, the amount of kind of loss or error I'm expecting is the following. And the way to get that is to get a brand new data set, which is you split it into a test set, then use that test set to evaluate the predictor, the model you got on your training set. And you get these points. So this is like how you would expect it to do on new data. And then you can be like, okay, I see. So it seems like the polynomial degree 3 predictor, right? This is the predictor output by ERM. This seems like the kind of the best choice. And this is going to look like a polynomial of degree 3 or less, right? It can't be more complicated than that. And so you would pick this. And maybe say a couple more. Like after running ERM with each one of these, you really have, here would be 7 different models, 7 completely different predictors. And you're trying to see which one is better than the others. And that's what these orange points are. They're an evaluation of those. Another way to think about this, more like, I guess, to match with things you might have heard, is you may hear of, like, there's all these different benchmarks that people, like, for instance, on these large language models, there's, like, these math benchmarks, and there's coding benchmarks, and you'll see the different, like, large language model companies, they all, like, have their scores on these different, like, there's, like, this MMLU and, like, Humanities Last Exam. Anyways, these are just names of, like, these benchmarks. They're just, like, kind of test points. They're like new testing examples. And all these large language model provider companies, the claim is that they do not have access to these benchmarks, this data. This is like your test set. They have no idea what that is. The company, these like benchmark companies, whatever, they do not publicly give it to anyone in the ideal world. And so these benchmark performances you're seeing in some way is the different models that have been trained by these companies, right? These companies run gradient descent for a very long time. They output this on their training set, which is however they got whatever parts of the internet they were able to get. And then the benchmark performances are like this LHAT of test, which is how they do on new data that they were never trained on, which is different domains that you can care about. There's ones for vision, like this would be classifying new pictures and things like this. And these are like these points. Okay, so we should probably end there. Let me just, yeah, same story, underfitting, overfitting. Next class, we're gonna kind of break this down a little bit more mathematically and what's commonly done. We're gonna see something called like this bias variance trade-off, which is what we've already been seeing. And yeah, all right, I will see you on Thursday.